these lectures here with the WIMP, and we're ending it here, misalignment, which is a way that axion dark matter can be produced. And those are kind of the two headliners, really. So it's good that that's the beginning and the end. And then the other things were sort of things between. And I tried to order the lectures sort of roughly moving through here geographically. We began with the WIMP was an example of a thermal relic where it is sort of similar to the standard model particles and that it has a lot of interactions and can be described using equilibrium properties of gases and can be described by a Boltzmann equation. And then we discussed a lot of variations of other things that are thermal, but structurally different from the WIMP, sort of exploring this part. And then yesterday, we started talking about non-thermal models, and these tend to have, unlike the thermal case, a very large coupling. Non-thermal will have weaker, more feeble couplings and not be in equilibrium. And we talked last time about things where the dark matter production was still tied to the properties of other thermal particles that you could kind of call from a thermal parent, be it decay or scattering of states in equilibrium, or a super WIMP, which Jonathan also talked more about, where it's a state that was in equilibrium, freezes out, and then makes the dark matter. That was all over here. And now today, we're going to be further away from that and really kind of far from, there's going to be no equilibrium properties at all. And in fact, today's discussion will be about dark matter that can be treated entirely in the classical limit. And it's just one example of classical dark matter, which is most famous, misalignment. And this is the idea where a scalar field can be produced solely through gravitational interactions that causes it to oscillate in its potential. There's other, I think, that you've heard about primary black holes elsewhere, and we'll hear more. We also talked about UV scattering. That's one way it can be produced at heating. I'm not going to talk about production from cosmic strings, but just be aware that misalignment is itself only maybe the tip of the iceberg in this broader realm of classical dark matter. Okay. Any questions about the big picture? Yeah.
I don't think we had time to get into this yesterday. Just a quick question on the oscillations from the thermal parent.
Yeah, maybe during this afternoon's discussion could be a good time for that. But unless it's really quick.
I mean, the small question was, I guess the mixing parameter must depend on the temperature, so it kind of.
Yeah,
okay.
It does. Yes, Stern neutrinos are a classic example here, but maybe this afternoon would be a good time to talk about that, or also this, or yeah. Okay. Good. So yeah, let me just make some general comment about particle versus classical limits before we jump in. Everything we've talked about so far, I would call examples of particle dark matter. And the sort of picture you can have, the cartoon you can have in your head is you can think of some co-moving box in FRW, and it's full of some particles that are the dark matter. And then we were studying ways to make that. In the thermal case, you actually start with a huge number, and then you dilute it down to the amount we see today. You can really think of it as a gas of dilute particles that maybe have some interaction. Its number density we've been describing using the technology of Boltzmann equations, where the production is sourced by the collision operator, which takes different forms in different models, but would be something like number densities times cross sections. And this, if this is all the dark matter and it's a particle, its mass needs to be larger than about a keV. This comes about actually from limits on it being too warm and free streaming, which other lectures will talk about. But just to kind of orient you, the WIMP would be much higher, say at TeV. But for particle dark matter, we normally have in mind masses above a keV. Okay, so that's sort of everything so far. Now I'll talk about dark matter in the classical limit. And then the cartoon can sort of change. You can still think about a co-moving box, but now you really have some coherent excitation of a classical field that you're studying that contains some energy, and you can no longer maybe be thinking about it in terms of individual particles. Yeah, so right here, I will mean dark matter and as coherent excitation classical field. And the way it gets around the constraints, in this case, on it being too warm, is it'll generally be bosonic and all in the ground state, all at zero momentum. So this picture will apply to bosonic dark matter at zero momentum, with large occupation number of the states. If you do think about it, in the particle picture, you'll see large occupation numbers, and that's why you can transition into a classical picture. And in this case, we'll be generally interested, roughly speaking, in masses much below an EV. There's not maybe a sharp definition, but we interested in really light masses far below this limit. And maybe between those numbers, you'd be sort of in a transition region. But then when you're below an EV and bosonic, you can normally think about it in the classical picture. Yeah.
So it's been a while since I thought about classical fields. Can we think of this as like a classical EM field?
Sure, that would be an example. It'll be here be scalar, but yeah, it's just a field that has a value everywhere and is evolving with time and contains some energy.
Okay.
And
Does the
then-
fact that it's a scalar field do anything different? I mean, I'm sure it does, but like.
Yeah, it won't have a direction. It'll just have a value.
Okay,
yes.
thanks.
So I guess if we're describing it as a classical field, why are we giving it a mass?
Oh, well, it will still be a particle at the end of the day. You don't need that, maybe that language, but I'm a particle physicist, so I'm going to want to know what's the mass, the axion. That's the thing you're tuning your cavity to. And yeah, so it's still useful in reality to move between both, but at least in terms of cosmological production, formally it can be treated in classical limit. But I'll always have in mind, I want to know what particle is behind that.
Sure.
Okay.
Quick question.
Yeah.
So in the particle dark picture with the very high masses, the number of particles now is very, very small compared to the occupation number of like classical dark. Is that right?
Yeah. So you'll have many less particles here, and they're heavier, and the energy will always be the same.
Okay.
Yeah, you have to match the energy, because the energy we observe, so we know what the energy density is, and then if you're hitting that energy density with a lighter field, it can only do that in the large occupation number limit.
Okay.
Okay. So I'm going to begin just with sort of a primer reviewing the behavior of a classical field in the FRW metric, and then we'll study its cosmological production. And the technology I'm now describing can be applied to the QCD axion, but I'm going to describe that technology in a more general way for an arbitrary scalar where the axion will be an example. Yeah.
How can this work that the sonic dark matter has almost no density but large occupation numbers? How does that?
Almost no what?
The rho is almost zero. Is that the density?
Oh, P. Sorry, I mean it's at zero momentum.
P.
Yeah, relative to the temperature of the CMD photons, more specifically. Yeah.
Yeah.
Sorry. Okay. So. Scalar fields. So in general, I have my usual Lagrangian for scalar field, which will have some potential, connector potential. The stress energy tensor in GR is sensitive to the metric, which in this case will be FRW. But in general, you can write, just to show you how the metric enters, you have some dependence on the metric that enters the stress energy tensor. So it takes this form. Now I'll be throwing the scalar into FRW, which is homogeneous, and therefore, in general, of course, the scalar field would depend on position and time, but in the homogeneous limit, it will just have a constant value everywhere in the universe, and therefore only be a function of time. Of course, you can add perturbations to that, but for the type of production I'm talking about, you can take the homogeneous limit in a Hubble patch. And it will in general have some initial condition that we can think of as being seeded by inflation, which will actually in general predict it to have a non-zero value, which can differ in each Hubble patch, but it will be from the perspective of our discussion, This will be an initial condition. But we kind of have in mind that it would be exceeded by inflation. So at t equals 0, we'll have value phi star everywhere in our part of the universe. Okay, and now the energy density and pressure of this field will be important because those are the fluid properties that will allow us to identify whether it is operating like matter or radiation. If we want it to be dark matter, it should have the fluid properties of matter. The pressure, the energy density and pressure are contained within this energy momentum tensor. And I'll now, this was in general, but I'm going to now specialize to FRW metric, and the energy density is given by the 0, 0 component of this. And it takes the following form, which you could guess. It just has a kinetic term and a potential term. Okay. And now the pressure will be the spatial part of the energy momentum tensor. Is related to the energy momentum tensor as follows. And in FRW, it is given actually by the same expression as the energy density, but the potential enters with the opposite sign. Okay. And now, if we want to understand how this field evolves over time, it'll evolve according to its equation of motion, which, and you know, for scalars, the Klein-Gordon equation, but you're interested in the Klein-Gordon equation in the FRW metric, which you may be less familiar with. So, equation of motion. And I'll just tell you the answer. It's phi double dot plus the h phi dot plus d prime phi, where you take a derivative of the potential with respect to the field value equals 0. So this looks like the usual Klein-Gordon, and then this term here is the new ingredient that the FRW metric gives you versus flat space. Okay, and now for the rest of the lecture, I'm going to assume that you're at a location in the potential where you're dominated by the mass term, which means I'll neglect higher terms in the potential, and this will be a good approximation in practice for, say, the axion later. So we're going to assume that the potential is given just by mass, but we'll allow this mass to depend on temperature. In general, there are finite temperature corrections to Lagrangian parameters. I haven't discussed them in these lectures. They're not important for thermal relics because you freeze out when you're non-relativistic, and then the finite temperature corrections are small. They actually are important if you want to do precise numerical treatment of things like freezing, where the temperature is on the order of the mother mass. And then in general, like their masses at finite temperature are different than masses at 0 temperature. And in the case of misalignment, we'll be interested in production when temperature may be much higher than the 0 temperature mass of the bosonic field. So tracking temperature corrections to this are in general quite important here. Yeah.
Is it possible at higher orders there could be interactions with the standard model?
Yeah, absolutely. But and usually they would enter by correcting this mass, and that's the way that it would enter here. And in the QCD axion case, QCD will create a correction.
Okay.
Yeah.
So for this temperature dependent mass, are we talking about like group level corrections, or are we treating this as some kind of effective mass given the temperature?
I think those two things can be the same, but yeah, I think both. I mean, there's an effective mass. It could get loop corrections. It could be non-perturbative in the case of QCD. QCD can give instantaneous corrections.
Sure. Okay.
But the sort of how to compute this in a given model is going to be beyond today's lecture, and let's just assume we know this and then ask what happens. Okay. So in that case, given this assumption that we're dominated by mass term, which means we're neglecting quartic or something, the potential now looks like this. So misalignment production is really just going to correspond to studying solutions of this equation. And right away, we can look at one special limit. At high temperatures, Hubble will be higher. Right? Hubble goes like T squared during radiation. And if Hubble will, at high temperatures, typically be higher than the mass. So let's consider the high temperature limit, which we'll define to be that Hubble at some temperature is much bigger than the mass at some temperature. Well, then we can neglect the potential in the equation of motion. It takes this form, and this has a solution just where phi dot equals 0. Kind of obviously that'll solve this, and that means that at high temperature, the field will be stuck, and this effect is referred to as Hubble friction. You can think of this as a strong friction term, and when it dominates over this, the field doesn't move. So Hubble friction by frozen, and then it'll just be frozen to have the value that we call the initial condition from inflation. So initially, when the universe starts and Hubble is big compared to the mass, this field is constant, and then only when the temperature cools enough that the field can start to see its potential, will it have the opportunity to begin to change value, and that's when interesting things will happen.
Yeah, but just we need this square place where
Thank you. Yeah, units.
Hmm.
Yeah, you can see. Okay. So that's all I want to say for this sort of general warm up for scalars. So now I'm gonna, when we've already started talking about misalignment, because we talked about the high temperature limit. But now let's ask what happens when this assumption does not hold. Yeah.
I'm not sure if this question even makes sense, but in the high temperature limit, could there be like a frozen excitation in the field where you could see a mass?
I guess you would need the mass to be as big as the temperature.
Okay.
But it won't be, yeah, and certainly not for the axion case that you typically need to go through the QCD. Yeah, so typically you'll be suppressed by couplings in a way that makes it smaller.
Okay.
So in cases I'm aware of, this is satisfied. But if it were not, then you'd have to think harder and have some UV production. Yeah. Okay. So next, let's talk more about the solution of this as the universe cools. Again, papers on this have a very long history, especially applied to the axion case. But for kind of a recent review, I'll recommend this paper because they frame it in terms of ALPS axion-like particles, so they sort of describe it in a more generalized way than just the case of the axion. So I think this is sort of in the style of this lecture. Okay, so we want to again look at the solution to this equation, and there's going to be two different limits. Kind of analogous in which there are two limits: a high temperature equilibrium and then constant. So for axion, for misalignment, there'll also be two limits. At high temperature, you're frozen. Yeah, so we've already said. So case one, much bigger than M phi. It's frozen. So if we draw potential this is the field value B, and the field is stuck somewhere because Hubble friction. And then the opposite case, where Hubble is very small compared to the mass. And then also, so if this term is not present, then what does this differential equation look like?
Oscillator.
Oscillator, it's a harmonic oscillator. So it's just gonna oscillate in the limit where you can ignore Hubble. And the sort of amount that the height of the oscillation will be set by the initial sort of energy contained here. And now it's oscillating back and forth. And then the fact that it's oscillating means it contains some energy, right? There's kinetic energy in it. So, yeah.
In the high temperature limit, what would set the initial condition to not be zero? Why wouldn't it be at the minimum, or not zero, but the minimum?
Okay, yeah, inflation will be happening at a high scale compared to the scales and the potential, and then the expectation is it sort of takes it a random value.
Okay.
But indeed the sort of details of inflation will be beyond this discussion for now. Okay. So kind of like the WIMP, there were two extreme limits, nothing's happening, equilibrium. Here are the two extreme limits are frozen, oscillating. The exciting thing is piecing these together. In the WIMP case, that was freeze out. And in misalignment case, it's the moment oscillations begin. And so we'll say oscillations start at a temperature I'll label T star. And the sort of analog of n sigma v equals Hubble for WIMP, where we use the sudden approximation, the sort of sudden approximation here is that Hubble T star is equal to the mass of the field at T star. And if you want to go beyond this sudden approximation, you need to actually numerically solve this. But for the purpose of this discussion, I'm going to take the idealized limit where it's frozen. At this moment, it oscillates and we neglect Hubble. So that's sort of the sudden approximation for misalignment. Now, if we assume this is occurring in radiation domination, we have the following expression from the first lecture. Like this equal to m phi. And that's T star. Therefore, T star is 0.78. T star to the 1/4 square root phi. I'm going to label this quantity m phi star, the value of the phi mass when the oscillations start. Okay. So at this temperature, we transition from Hubble friction regime to oscillation regime. Okay. Now the equation of motion can be solved using WKB approximation, and I'm gonna just jump to the solution. It sort of takes the obvious form of an oscillator, except if there were no Hubble, it would just be exactly an oscillation with constant amplitude. So the fact that this term is present means that the amplitude, it's an oscillator whose amplitude can slowly vary, or like an oscillator with friction, obviously. So we'll have phi of t equals a of t. Yeah, so here we're in the limit h much less than m phi. Cosine alpha t or alpha t. Integral t star to t m5t. So it's just an oscillator. The two subtleties are that the amplitude, because of Hubble dependence, the amplitude can slowly vary with time. And as we've discussed, the mass, we're allowing to depend on temperature, so the frequency of oscillation can slowly vary with time. But in the limit, that Hubble is much smaller than the mass, those are the variation of the amplitude and the mass will be slow relative to the oscillation frequency. So you can go for many oscillations and think of it as having constant amplitude and constant frequency. But then over time's long compared to the oscillation time, those two things will drift in a way that would be captured here. Okay, but yeah, so phi. Oscillates with frequency omega equals phi, which is time dependent. Yeah, and importantly, in this limit where Hubble is much less than m phi, the A of t will be slowly varying. And quantitatively, what this means is A dot over A is much less than m phi. And that's just sort of integrating out the two different time scales. The time scale Hubble is much slower than the oscillation frequency, so the amplitude will vary much slower than the oscillation frequency. Yeah.
What about the second solution in the case of high temperature? I mean, you just pick up the solution for phi being constant, but there was another solution which would go at an exponential at a decay, so at a decaying at exponentially e to the minus 3 times h times time.
Let me think. Yeah, I'm not sure why I'm picking this one. But you're saying that there's another solution where it just disappears.
Yes, if we assume that h is constant during this time, then you would have a simple solution e to the minus 3ht.
Yeah, it's not constant, but yeah, so I'm not sure is the answer.
Go away. I mean, it's essentially.
Yeah, it would just go away. So and then maybe, but then maybe you're just left with this. But why pick this? I would have to think about. Yeah, I'm only claiming this is a solution. Then it's a solution I'm studying. Yeah, whether there's other solutions is very interesting.
Would the amplitude have the same temperature dependence as the Hubble rate?
In general, not. And here I'm just going to need the fact that it's slow. In fact, we'll see the dependence in a moment. That'll follow from yeah. So maybe wait, and I'll get to that in a second. Yeah, we'll see how the modes vary with time. Yeah.
Yeah, so I guess mine is kind of it's a question about notation because the mass of phi is temperature dependent. But temperature depends on time, I guess. So the t in the alpha is small t time.
Yeah, this is time, but time, there's always going to be some mapping between time and temperature, so you can choose whichever variable you want. It's just that, as I've written this solution, it's time that enters the integral. Okay, so yeah, this will be important. And now, if we want, I want to ask what are the fluid properties of this oscillating solution. So we should look at the energy density and the pressure, and if we're interested in the sort of cosmology, that because Hubble is much slower than the frequency, we can average over many frequencies and then look at these quantities, energy density and pressure. So I'm going to take averages over the oscillations. So I'll write that like this. And the average of the energy density is 1/2 average phi dot squared plus 1/2 average. So you can just plug this in and average, and then you will find 1/4 A dot squared plus 1/2 m phi squared a squared. You actually pick up this piece and this piece will have the same size, so you kind of get half of this from there, half of this from there. And then if we use this approximation, we can neglect this term, and the energy density will be dominated by this piece, which is kind of half coming from kinetic and half coming from potential. Okay. And similarly, we can look at the time average of the pressure. And this flow is the same as this with a minus sign. But half of this came from here and half came from here. So with a minus sign, this part cancels and you're just left with this. And therefore, if we form the equation of state, which is pressure over energy density, and this goes to 0 in this limit that the amplitude is slowly varying compared to the frequency. And zero equation of state, pressureless fluid is the equation of state of non-relativistic gas. So that wouldn't have been obvious to me a priori. This coherently oscillating scalar field from the sort of fluid point of view, which is what the cosmology sees, behaves in the same way as an inert gas of massive particles.
Sorry to recall back to this, but on this second solution, this decaying, are we not interested in this decaying solution? Because then when I stitch together into this second region, I would probably be stuck at phi is equal to 0.
Yeah, I'm not sure if there is a second solution. I'd have to think.
The decaying solution exists.
yeah.
If we choose that, then we would sink to 0. And then when I evolve to this Hubble is much less than m5, wouldn't I just be frozen at 0? And
Yeah, it wouldn't have any energy. So you would only be left with non-decaying solutions at late time. That's
Right.
certainly true.
Right.
I agree with that statement. But
Okay.
but whether there's another reason to discard them. I'd have to think.
Well, I mean, you can think of it in a more general way. I mean, you're looking at a solution where you neglect m5, then
Yes.
not do that, so you have two solutions.
Sure.
So the general one is the sum of the two.
Mhm.
The one that is exponentially decaying is irrelevant.
Yeah, I agree.
Yeah.
You're dominated by the one that stays.
you're-
Sure.
Yeah.
But is there a way like to somehow make it all decay and remove the energy?
Well, you
Would
can
it-
fine tune the initial conditions as it will only be in the other one.
Sure. But if I start at phi star, can I do that?
That's that, as soon as you do this, and it's almost at rest, you're done.
Yeah, good. Thank you. Good. So the inflation doesn't only pick the initial field value, it picks the initial velocity. Good. So this decaying one, the initial condition will remove. Thank you.
The velocity of what?
The field phi.
Okay.
Yeah, the field phi has an initial value and it also has an initial velocity. So I was sort of implicitly taking the initial velocity from inflation small in this discussion. Yeah, okay, that was the solution. Thanks. Okay. Good. But yeah, so initially we're taking phi 0. Phi star, and we're taking phi dot 0. This is a more precise way of saying what I'm assuming. Thank you. Okay. So equation of state of matter, which makes this a dark matter candidate. And let's look a little more carefully at the energy dependent, at the time dependence. Ask, how does rho find? All the time. Does the energy density behave like dark matter? It kind of has to because of the equation state, but let's so we have rho phi 1/2 phi dot squared. That's time derivative, tells us about how it's evolving. Phi dot, double dot. Phi squared. Phi dot. Plus m phi. Phi squared. And then we can plug in the equation of motion to remove phi double dot in terms of the other terms. And we get phi dot that squared plus m phi dot phi phi squared. Okay, so here we're just looking at the energy density, assuming it solves the equation of motion. Now, if we look at the time average of the time derivative, then we just take the time average of this. Okay, and now, well, before this piece here, half of it came from here and half came from here. So if we neglect the A dots, then we can approximate the average of phi is equal to the average. Phi dot squared is equal to the average of phi squared phi squared. All of these are equal 1/2 m phi squared a squared. Okay. And therefore, we can divide by this object. So I'm going to divide this equation by this object, and then I arrive at the following equation. Right, how the energy density evolves. Here I'm just writing now Hubble in terms of the scale factor. Okay, and the solution of this equation takes the following form. The phi energy density per mass is conserved per Coulombic volume. The times a cubed. It's constant. So this will tell us how rho phi evolves with time, allowing for the time dependence m phi. Okay, and so far I'm just talking about the classical field, but it will be made of particle quanta. So the number of particle quanta, I'll define to be this object rho phi per mass, and we see that this scales as a to the -3, just like the inert dark matter particles do, so that they just dilute. The quanta just dilute with the scale factor, and therefore the number of phi per entropy density is constant, just like the yield quantities that we saw in the context of thermal relevance. So it's really acting like dark matter. It's pressureless. It has the equation of state of dark matter. The quanta are redshifting like dark matter particles, even though the picture is very different. Now it's just coherent scalar excitation. Yeah.
Are we doing a classical quantization here? Or are we just ignoring QFT basically?
Well, it comes from QFT. So I don't know, but the solution here is dominated by the classical limit. Yeah, and they're all at zero momentum, so there's no H bars.
Okay, all right. So there is a canonical quantization happening. We're just looking at the limit
Yep.
where it's classical.
Yep.
Okay, thanks.
Okay. So that's sort of the misalignment primer. And I now would like to describe the form of the energy density, like and ask what parameters will match the observed dark matter energy density. We're just using the fact that the time average energy density is given by this, then we just want this to match the energy density of dark matter that we observe.
A small question. I don't know if I understand the terminology of misalignment. Are we just talking about the initial position?
Yeah. I guess so. So by star. Yeah.
sure if I understand how to relate this to the cosmological perturbations in dark matter that lead to landscape structure and the features in the CMB, like how if this fields classical, I don't see the connections. Like
This, the perturbations will be the same for this or for a particle. It is called dark matter because that can all be described in the classical limit. And I assume Anne talks about this in her lectures, but it's really the same. It gravitates, it'll have some initial condition of regions of higher and lower density when you add now small perturbations. So that picture can be treated in the fluid limit and applies therefore equally for this type of model or any of the models I've talked about. Okay. So. Again, my goal in this section is going to be to arrive kind of at an understanding similar, like in the WIMP case, we had that omega was 1 over T equality and Planck sigma v, and then this should be order 1, and then told us the size of sigma v. I want to have kind of like arrive at expressions like that, but now for misalignment, and then kind of ask what should the properties of the scalar field potential be to that. So omega is order 1. Okay. So, well, the general expression for relative density that we've been using in all of these lectures applies equally well here. If we want to keep the order 1 numbers, we can write it as entropy density today. The critical density is prefactor times the mass. Times the number density per entropy density. Should be 0.12. But this is the energy density today. So this would be the mass today at 0 temperature, close to 0 temperatures. That'd be sort of the bare Lagrangian mass is what we're seeing now, which is different from the mass that we called M phi star when the misalignment occurs, but just this we want to be satisfied given this type of evolution. Okay. Now, so we argued that n phi per s is constant, right? The co-moving number of quantum is constant, and therefore we can evaluate it at the moment misalignment begins, which would be the analog in the WIMP case of evaluating number density per entropy at the freeze out moment where we know its value. So this will evaluate at the temperature where Hubble equals the mass, where, if you remember, this was given by the following. Okay. And the number of phi was this oscillation averaged energy density of phi per mass, evaluating it when the oscillations start. And then from our result before, that was just 1/2 phi times the amplitude, a phi squared. Okay. And now in practice, certainly when we get to axions, we'll be interested actually in a theory with a cutoff scale. In the axion case, it's called F, a scale of say Pechi-Quinn symmetry breaking or something, but there'll be like maybe some UV scale that characterizes the dynamics of this field. So the convention is to write the initial amplitude in terms of some scale. So I'm going to take A star and I'm going to, this will be defined to be a parameter theta 0 times some scale that right here is F, which is a characteristic scale of the potential. Scale of potential. And then this, we would expect from it, this is a random order 1 number would be our expectation from inflation. So and this is often called the phase. So the random. Starting phase. We expect theta 0 to be order 1 in the absence of fine tuning. Yeah.
And why would we expect that for inflation?
Well, just that you're at a random spot in the potential relative to the cutoff. It'll pop different Hubble patches. Will just take different values that sort of uniform over the scale the field evolves over. Okay. So, right, just with this notation then, n phi star is 1/2 m phi star theta 0 squared f squared, plugging in this. Okay, and then we'll also need this entropy, which is 2 pi squared over 45 g star s t star cubed.
So we have a question.
Oh, yep, please.
Hello, can you hear me? I have a question. So
Can you speak?
I have a question regarding this temporal or temperature dependence of mass parameter. Is this free to choose? In this
Which model? You're asking, are you free to choose the temperature dependence of the mass parameter?
Yes.
Yeah, and that'll be model dependent. And for now, I'm taking it as an arbitrary function, but I'm gonna, in the last part of the lecture, apply this to the QCD axion where there's a predicted form for this temperature dependence.
Okay. Okay. So then you will state some example of it.
Yeah, I'll give an
Okay, great.
example.
Perfect. Thanks.
You could even, it could even be that that has no temperature dependence. So maybe let's take the simplest example would be it's a completely decoupled scalar that has a mass and then only interacts gravitationally with everything else. That would be like the simplest model of dark matter you can imagine. And then temperature dependence could be trivial. So that'll be my 0th order example. Let's just pretend that it's a constant. And then I'll give an example where it's more interesting, applied to the QCD axion in a minute.
Okay. Thanks.
Okay.
What is the theta 0? Is it phase?
Yeah, and the reason I'm using that language is in models like the axion, there's a shift symmetry, and then you can describe it in terms of a phase of a complex field. But really, for the point of view of this discussion, it's just a parameter. So I'm just defining an order 1 number times some cutoff scale.
Okay. It's not a phase. I'm like, I think with the axion it can be a phase, but it's not really a phase. Like, it's not like an HDI omega. Like
Yeah, no, it's not a phase in terms of this motion.
Okay.
It's a phase in a different field space that yeah, we don't think this word really. Okay.
Okay.
Just you'll read in the literature the word phase for this
Okay.
misalignment phase, and then okay. Okay, so plugging in this and this into here, we arrive at an expression for the energy density. Okay. We arrive at the following. We're here, unlike in the WIMP case, M Planck only entered in one location when we said n sigma equals Hubble. And here, well, here it's entering in a slightly different way. It's entering through T star, which sets when we start to oscillate. Okay, so we get this. But even though I put two digits here, that's sort of overstating the accuracy of this, because the approximation that I'm making is I'm still using this sudden oscillation limit, right? I'm evaluating the energy density when Hubble equals mass. But then when I describe to you this oscillation with the slowly varying amplitude as the solution, that's the solution in the limit where Hubble is actually much smaller than the mass. So I'm extrapolating the low Hubble solution to the moment oscillations start and then plugging into relic density. So this is really going to be an order one number here that where you'd have to kind of carefully solve the equation numerically to get it. So it's a really sudden, it's the analog of sudden freeze-up approximation, which also is only good at a factor of 2 level. So this is the sudden misalignment approximation. But if we want to even be more approximate and use Josh given units where we neglect numbers, then we write this prefactor we just called 1 over temperature maturation equality. Remember that was good actually within a factor of 2. And I would write the following expression. So let's just emphasize the parametric dependence. We arrive at this. And this should be order 1. Yeah. Thank you. Okay. The units would have been right. You are correct. And this gives you a relationship now. So we have 2 cosmological parameters, and then we have a relationship between the phi mass and F. And I've been careful to keep separate the phi at 0 and the phi at T star. If we were in the model where it was constant, then we can set those equal and simplify a little further. Okay. So this is the sort of analog for misalignment of the famous 1 over T equality M Planck sigma B expression we had for thermal relic would be this. And here it just depended on cross section. Here it depends on the mass of the field and its amplitude, which we encoded with these 2 parameters, but that's just the initial amplitude. Okay. So that's the energy, that's the relic density from misalignment. Any question? Yeah.
When we do this, when we look at the yield and we say Fi per S and evaluate it at T star, can you tell me again why we're evaluating it at T star to get a relic density?
Because the co-moving number density after that is constant, and we know how to relate T star to the mass.
Okay.
So it allows me to write this all in terms of like properties of the phi potential.
Sure.
But yeah, to me, morally, it's kind of like, why do we do, if for the thermal relic case, you could evaluate it at any time during the solution of the Boltzmann equation, but it's nice to evaluate it at the freeze-out moment, because then at that moment, there's a relationship between Hubble and cross-section. And here, at this moment, there's a relationship between mass and Hubble. Yeah.
You define this like interpret, like if you make the width comparison, then this interpret, so sigma V is something like a ratio of masses times these coupling constants. Like,
Yeah, in a say classic example, this would be some alpha squared over m squared that you can plug in here, and then we would have some m squared alpha squared. Yeah, so it's really different depending on things, different scaling within Planck, for example.
so it's not like a good analogy of that.
Oh, by analogy, I just meant these equations play the same role.
Oh, okay,
Sorry,
but they're fundamentally different.
but they're very different,
Okay.
extremely different, wildly different scales,
Okay,
and it's pointing to very different masses, interactions, experiments you look for.
okay, so the idea of a process doesn't really apply to this classical treatment.
Yeah, no, here, all that enters is the mass and F and the temperature dependence of the mass.
And I guess our potential interactions in the standard model are encoded in that temperature.
Yeah.
dependent mass? Okay.
Exactly.
Yeah, to say that that phase, the initial value is random, and we can get like an axion-like particle. Are we assuming that that scale is above the reagent temperature, just like otherwise it would be the average. I want this paycheck fee to be broken only during inflation and not.
Yeah, I get confused. Yeah, the treatment varies depending on when Pechiquin is broken before or after inflation, and this applies to one of these two. I guess the case where it's broken and then inflation happens.
I think it's random when it's broken during inflation.
Yeah.
Not restored after.
Yeah, I think I agree with you. Yeah.
So T reading should be less than the scale of potential. If I say that it's.
Well, yeah, more precisely the scale of inflation versus Pechiquin scale. Yeah, reheating is a third thing because then there's a couple of interactions that could happen.
Okay.
Yeah.
So I know we're not talking about mass dependence of phi, that would be model dependent. But I guess we're saying that this thing can't decay or its decay is suppressed enough. Right?
Yeah, I mean that sort of any of the models I've talked about, you could have some slow decay. And then for it to be a good dark matter candidate, it has to be longer than the age, live long the age universe, and then in the case of standard particles, much longer than that even. That is actually a very interesting constraint in axions where you'll have phi to gamma gamma. But the F's that you'll need are quite big, and then this can be slow enough. And well, in the next part, I'll do pick axion as an example and look at the scales. But this being metastable is a real issue. Yes.
Sorry, this is what people typically call fuzzy dark matter, right?
Well, fuzzy dark matter is where you saturate the lower bound, where the de Broglie wavelength is kiloparsec. And this is a way of making fuzzy dark matter. This is more general. If so, fuzzy dark matter would be where this m phi 0 is like 10 to the minus, what is it, 22 eV or something? Yeah, 10 minus 22 eV.
Yeah, but that's what surprised me because in this calculation we could always neglect like kind of quantum effects. But I heard that for fuzzy dark matter, sometimes people need to consider like we have some kind of wave function with macroscopic size.
That's when you describe its properties in a halo.
Okay, so then the quantum effects are important. But here,
I'm not talking. I'm talking about homogeneous production in the universe, and fuzzy can be produced using this misalignment. Yeah, then when it collapses into galaxies, if the de Broglie wavelength is on the scale of the halo, then you have to
of
worry
course,
about
here
things
there's
like the
no
soliton.
okay, okay.
Yeah, but yeah, that's within the realm of now plugging into halos, which are another lecturer, I assume. Okay. So we've described misalignment in general. This you would call an axion-like particle or ALP, in the sense that you haven't demanded it be the QCD axion so far. And I'm going to now apply this technology to the QCD axion, which is the most famous application of this idea, and really the idea was first discovered looking at the QCD axion, and then its generalization, the way I presented it here, is more recent. Okay. And I assume that, Yuri, I assume later there'll be a lot of axion lectures
Yes.
after I leave. So I'm going to give a very quick intro because I'm probably the first to talk about it, and then you'll hear much more later. So it's a big subject, but the QCD axion is motivated by the strong CP problem, which I will very quickly say. The QCD field strength, the CP violating interaction you can write with QCD, where this is a free parameter, which if it's non-zero violates CP. And naively, you would expect this to be order 1, but it generates neutron EM, and bound the neutron EM constrain this to be smaller than about 10 to the minus 10. And so the why is this not order 1 is called the strong CP problem. And the axion is a proposal for solving this, where you add a field that couples to this CP violating interaction. So A is the fields of what I was calling phi before is now A. And then it couples to your high dimension operator to this. The QCD confinement generates potential for A, and at the minimum of the potential, it will cancel this and set this to 0, and then explain why sort of dynamically explain why we don't see neutron EM. So the A potential today will be at the origin. Okay. But A can be produced through the misalignment mechanism that we've been describing. And is therefore, besides this, it could do 2 purposes. It can both solve this strong CP problem and be a candidate for dark matter. QCD generates an axion mass, axion potential. So at t equals 0, it is approximately given by the following expression. These are quark masses. Ion decay constant. And so this FA is some high energy scale that you would take in a UV picture to be the scale of Pecha-Quinn symmetry breaking. And then we see the axion mass is small because it's suppressed by this QCD scales over this high scale. Yeah, and this numerically is sort of milli-electron volt. If we take this scale to be 10 to the 9 GeV, which, as we'll see, will be an interesting number from the cosmological point of view. Yeah.
Is it important in the context of this lecture to understand like how QCD generates?
No.
Okay, thanks.
Because somebody will do this later, right?
Yes, yes, those will have a long.
Okay, yeah. It would take me much too long, so for now, just take my word for it. But it's coupling to the gluons, QCD confines, stuff happens, axion gets a mess. Okay, yeah, and numerically, but yeah, what we plugged in here, 93 MeV is the pion decay constant, pion mass, 40 MeV. These are really, if we wanted to be more schematic, we could say, for the purpose of a rough estimate, these are all the scales of QCD. So F pi, M pi, sort of the scale where the strong coupling becomes strong, which is sort of the 100 MeV scale. Is sort of the scale entering here. And therefore, we can sort of say just schematically, yeah, this would be order 1. So the mass of the axion is sort of given by the QCD scale squared divided by this high energy cutoff would be the kind of quick way of thinking about it, if you don't care for order 1 number. Now, that's 0 temperature, but the temperature dependence is crucial for misalignment. And in this case of QCD, instantons, will generate a non-trivial high temperature dependence. And this will go like the 0 temperature mass. Yeah, I'm gonna, if I don't write this, then just assume it's 0 temperature. So I'm not gonna write a 0. And the mass will be suppressed at high temperature, like 1 over temperature to the 4th. And I'm not going to explain now where that comes from, but that's what we think instantons will do at finite temperature. So at high temperatures, it'll be much lighter, and then this will be much smaller than this. Okay. So you'll hear much more about these ideas later, and now I'm just sort of introducing some results to make you aware. Yeah. Non-perturbative stuff in QCD that changes the mass. Is that good enough? And you'll hear more later, which lets me move on. Okay. So now what I want to do is plug these results into this expression and then figure out what scales will work for this being the dark matter. And dark matter. Misalignment. Historically, this is how misalignment was discovered, and it goes back to the early 80s. Pascal. Check. 1983, where they discovered the misalignment mechanism when they were interested in axions. Okay, so I want to take this as the starting point, and then I'll just write it again over here. Now putting A's is what it's the axiom. Okay, and MA0, whatever, yeah, which I'm just calling MA. We argue was lambda squared over F. MA star is the value of T star, which is now MA lambda T star fourth, where, and I'm neglecting the order 1 prefactors, so I'll just write this as square root MA star M prime. And you see MA star, well, it appears on the left-hand side here, but T star also depends on MA star, because T star is defined to be when Hubble equals MA star, so there's an MA star hiding in the right-hand side of this equation too. So we can now solve for MA star, taking into account that it's also appearing in here. So I'm going to plug this expression into here, solve for MA star. derive at lambda squared over FA to the 1/3 and Planck to the 2/3. Okay. Where again here, I just plug this in here and then solve this for MA star, make it this.
So here the only like axiom specific thing is this introduction of instantons. Or something else that.
Well, there's 2 steps. Yeah, there's the this is lambda QCD. So this equation and this equation are the 2 steps. Yeah.
Okay.
So the 0 temperature mass is lambda QCD squared over cutoff, and then the temperature dependence is lambda QCD to the 4th over temperature to the 4th. So both the 0 temperature and the instanton result, these are the 2
Okay.
places QCD is entering, and then that allows us to relate the mass, to F and lambda, so lambda QCD and cutoff. Yeah, whereas before when we were in out, we only had a cutoff here, and there was no and a mass. So now we can write it in terms of cutoff and lambda QCD. Okay. So that's all we need. So we plug this to here, and we plug this to here. Yeah. Both of it. Right back. Back of the envelope axion energy density. Okay, 7/6. Okay. Yeah, and again here, the reason that F is entering with a different power than here is that the QCD axion predicts a relationship between the mass and the cutoff, and then lambda QCD as it enters as a scale also. Okay, so we want this quantity, if it's all of dark matter, should be an order 1 number, and this relates the lambda QCD we know to be 100 MeV. So these are known from cosmology. This is known from the standard model, and therefore there's if we assume theta 0 is order 1, there's just one unknown, the scale F, and then we can predict what scale would give the observed energy density for misalignment. So this we solve for FA. Theta 0 minus 12/7 T equality over lambda the 6/7 and Planck, and then plugging in for these parameters, I find theta 0 is the minus 12/7 times 10 to the 12 GeV. Okay, so that's the scale we need. Sort of the Witt miracle version for axions from misalignment is 10 to the 12 GeV. So it would give order 1 omega. Yeah.
So what's so miraculous about this number?
It's a cool number, 10 to the 12. Why not? What's so miraculous about 100 TeV?
Well, I don't know, with the, I mean, at least with the Witt miracle, it's like, okay, everything's weak scale. Here, we just say, okay, I must have this F that is this number to give me everything. And I don't know. I mean, it seems like when we had the strong CP problem in the beginning, we had this bound on theta, it must be this small. And now we solve it by saying that this number must be this big.
Mhm.
I don't know, it doesn't seem,
There's no problem though.
seems like.
But indeed, this is not a scale a priori that we see in the standard model on like the WIMP case. That's true. But it points to some scale. Yeah.
So does this not seem like a fine tuning?
No, because your UV model can easily be technically natural and have something happen at this scale, and that's far away. And there's no parameters being tuned. But there is a case for fine tuning enters here, which is suppose we want f to be bigger than this number. And indeed, like suppose we want to align this with a scale that we do that is motivated independently. Like that, you could consider f far above this if you fine tune theta 0 to be close to the origin. Okay. So FA much bigger than 10 to the 12. GV is possible. With the tuning theta 0 much less than 1, which is kind of equivalent to saying you tune it to start close to the origin relative to the cutoff, and then you keep the energy density small. And this is interesting to contemplate, because then, for example, you could take this to be something like the gut scale out at whatever 10 to the 15, 10 to the 16 GeV or beyond. And then you could kind of connect it to something where it's independent motivation. And also these very high F axions, as you make F higher, the mass gets smaller, where the wave gets bigger, and then you hit the size of astrophysical objects like black holes. So axions in this window can be tested through a mechanism called black hole superradiance, where they can spin down black holes. The fact that we see evidence for spinning black holes can place bounds on this region, but you would generically expect these to predict too much dark matter, because F is too big, right? Increasing omega. But then if you demand did not produce more than the observed dark matter, you can achieve that by tuning this misalignment angle close to the origin, and then contemplate these high F axions. And even some people, I mean, you can motivate this by saying maybe observers require there not to be too much dark matter. So this window here is sometimes called the anthropic axion window. So maybe observers find themselves in Hubble patches where the misalignment angle is accidentally small, so that there's not much more dark matter than we see. Yeah.
There are any constraints.
On what, sir? When the theta just enters through the relic density, so the constraint is just the relic density. F, there are many diverse constraints, because that sets the coupling of the axion. So before people asked about lifetime, and also, well, generically, these axions are produced, for example, in stars and other experiments. So there are sort of bounds requiring to be bigger than about 10 to the 9 GeV from energy loss in stars. And then there's a nice window between there and here where it would sort of be allowed by experiment, and then not too much dark matter. And then once you hit 10 to the 12, it's all the dark matter, and then above that, you're tuning misalignment. Yeah.
Yeah, I thought the whole point is to all of this thing is to, because there's a theta bar, right?
Mhm.
You try to avoid fine tuning, right? I think it be cancelled by your A over F A. Then now you still have to fine tune your F A by tuning your theta bar.
Yeah, only if you want to enter this regime far above 10 to the 12. So if you stick it at 10 to the 12, you don't have to. If you want to go to F's far above 10 to the 12, then you're right. You're moving the tuning from one place to another. But for the GG dual, the tuning was 10 to the minus 10, whereas in practice here you only need a few percent to tuning to bring this small enough. This 12/7 helps a little bit. Yeah, so a few percent tuning can work here. So it's not too.
remind me, why you want to be in the regime, the FA greater than 10?
You don't have to want that. You can just be happy with 10 to the 12 and not talk about tuning. But if you want to, if you want to not only do two things at once, solve strong CP and explain dark matter, but if you're really ambitious when you wake up and you want to also connect those solutions to grand unified theories, then maybe you want to push it up to here. Yeah.
This data has an integration of an angle, like an angle with respect to what?
If in like a model of Petrikman symmetry breaking, this could be a complex field with a radio mode and an angle, and then you could think of that in terms of an angle.
So when you said it was small, then you put the, I guess this is what, like potential versus field?
Yeah. So sort of there's a typical field size out to F, and then you would expect inflation to uniformly sample it between 0 on scale of F. So for the amplitude to start at a value far below this cutoff would then be an accidental patch from the point of view of an inflationary model is random sampling.
But F being bigger, does it not give you more places to sample from in the field for the initial field values?
Yeah, but yeah, but then if theta is over 1, then F being bigger makes the energy density bigger.
All right, okay.
Question from the chat. So, Joseph,
I have
You
a
wanna-
question. Yeah, I have a question because this is a result of a specific choice of our initial Lagrangian, right? So if one chooses much different Lagrangian, how much can one change these constraints of cutoff scale and angle? Can one get, for example, 10 to the 9 or 10 to the 20 or?
Sorry, I couldn't hear. You said it's a specific choice of model, I think, by saying it's coupled, but by saying it's a QCD axion. So you're asking how model dependent?
Yeah. So how Lagrangian dependent, how model dependent this result is?
Very. And here also the statement that there are experimental bounds at 10 to the 9 GeV is really relying on assuming it couples to GG dual and also typically to FF dual. So the experimental bounds are very sensitive to how it couples to the standard model, and then if the temperature dependence of the mass here this T to the 4th was particular to QCD instantons. If it's like a hidden sector that's purely weakly coupled, the temperature dependence could even be trivial, or and then the scales could be quite different. So from the point of view of misalignment as a mechanism, this is a very specific example. And then these constraints are very specific, but it's the one everybody likes.
So would you say that, for example, this constraint of F being greater than 10 to the 9, you can rule out a sufficient amount of models, or this is just too weak?
But it's very interesting constraint. Yeah, there's a large realm of models that would have solved the strong CP problem, where we should be now playing with axions in the lab. So it is very interesting, but there's also a region where they're viable where we're looking. So it's a big. The idea of an axion where you vary the scale F is a very big idea in the sense that there's a broad parameter space.
Okay, thank you.
Sorry, so I mean, this operator with the axiom is a dimension 5 operator. Now, are there any problems concerning like also, I don't know, the QCD renormalization, or because don't you introduce something else than in your QCD beta function through the axiom?
Oh, but it's such a high scale, it's not going to affect them.
Yeah, okay, yeah.
It's not affecting anything in QCD, I think. I mean, the way it affects it is you now have this new light degree of freedom that you can look for experimentally, but beyond that, okay. Yeah.
I got a bit lost before with the naturalness discussion. Just as I understand, you don't have any problem having like small parameters if you have like a bigger symmetry. But in this case, CP is also not constructed in good interaction. So I'm not sure what's going on here.
Yeah, these are interesting issues. Yeah, so we have this theta GG dual, and then we say there's this bound theta bar less than 10 minus 10, and then you could ask, is a small value technically natural or not, I think is what you're asking. And the answer is actually, accidentally, the answer is yes, unfortunately. And it's a bit subtle. I mean, so normally the rigid way we would say it's like technically natural if a symmetry is restored as it goes to 0. And as you say, the weak interactions violate CP, so symmetry is not restored as you send this to 0. But you could flip it around and ask, suppose I start with it 0, given the CP violation and the weak interactions, they should feed in to theta bar. How much do they generate for theta bar? And it turns out in the standard model, this the weak CP enters this very weakly, like at 3 loops and suppressed by masses. And if this starts small at the cutoff, the CP violation, the weak interactions doesn't spoil it being small. So it's sort of accidentally technically natural for this to actually be small at the cutoff, and then you wouldn't need an axion. And there are solutions that try to use this fact and to set this to be small in the UV. And these are called, for example, Nelson bar models, and they have no axion. And you just start with it small, and then you use this fact that the weak interactions don't generate it. If the standard model itself generated a large correction to this, then axions would be a much more compelling idea. But unfortunately, it doesn't. Although many UV completions do, and so it's a bit actually a bit rich answer. Yeah. Any more? Okay, if not, we'll have time for questions this afternoon. And, thanks for coming and asking so many questions. It's my first time teaching partly in person for a long time. So it was
Well, thank
fun.
you, Josh. Yeah, so just a reminder, there's a discussion session at 5:30. And I think it's gonna rain, so. Just in case, we haven't talked about this yet. I don't know, so it's the same as before, no? So you ask any questions, and I'll do this dial up, dial down with the button. I think it's still faster. The other option is we take the microphone and it goes around, but then